For 70 years, flying cars were a punchline, the broken promise of every futurist magazine cover since 1950. But right now, in a hangar in California, a 4-seat aircraft with no wings, no propeller, and no pilot training required for regulation-grade autonomy just completed a piloted flight over Manhattan. This isn't science fiction anymore. This is engineering catching up with a century-old dream, and it's closer to your driveway than you think. Welcome back to Engineered Future. Today we're going inside the real engineering behind flying cars. Not the concept art, not the hype, but the actual physics, the actual regulations, and the actual companies racing to put electric aircraft over our cities within the next few years. We'll look at why every flying car attempt of the 20th century failed. We'll break down the technology that finally made it possible. We'll meet the aircraft currently flying test routes today, and we'll be honest about the biggest obstacle left, one that has nothing to do with the aircraft at all. This is the story of how flying car stopped being a joke and started being a certification checklist. The dream is almost as old as the automobile itself. In 1917, Glenn Curtiss unveiled the autoplane, a car with detachable wings that never truly flew. In 1949, Moulton Taylor built the Aero car, a genuine roadable aircraft that could drive on highways and fly through the sky. It actually worked. The FAA certified it, and it never sold more than a handful of units. Decade after decade, the pattern repeated. Engineers built something that could technically fly and technically drive, but never something practical, safe, and affordable enough for ordinary people. The problem was never imagination, it was physics. A car engine is heavy, and it's tuned for torque at low speed. An aircraft engine needs to be light and tuned for sustained high-speed thrust. Combustion engines simply could not do both jobs well in one machine. Every flying car built on gasoline power was a compromise. Mediocre in the air, mediocre on the road, and often dangerous in both places. For the dream to work, engineers needed an entirely different kind of propulsion. They needed something that didn't exist yet, that something arrived from an unexpected direction, the smartphone and the electric car industry. Two breakthroughs changed everything. First, lithium-ion battery energy density improved dramatically over the past 2 decades, driven by consumer electronics and companies like Tesla. Second, and more importantly, electric motors solved a problem gasoline engines never could: distributed propulsion. Instead of one heavy engine driving one propeller, an electric aircraft can use 8, 10, or 12 small, lightweight electric motors, each spinning its own rotor, all controlled independently by flight computers. This is the core engineering idea behind almost every modern flying car, properly called an eVTOL, short for electric vertical takeoff-and-landing aircraft. Distributed electric propulsion solves 3 problems at once. It removes the need for a runway, since multiple rotors can lift the aircraft straight up like a drone. It builds in redundancy, since losing 1 or 2 motors out of 12 doesn't bring the aircraft down, and it dramatically cuts noise compared to a helicopter's single large rotor, because the load is spread across many smaller, slower spinning blades. This is why, after a century of failure, engineers finally have a real path forward. Not a car that flies, but a purpose-built electric aircraft that can operate almost anywhere. So what does one of these actually look like? Joby Aviation's aircraft, the S4, is the clearest example. It seats a pilot and 4 passengers, uses 6 tilting rotors that point upward for takeoff and rotate forward for cruise flight, and has a top speed of roughly 200 miles per hour with a range of around 100 miles on a single charge. In flight testing, Joby says the aircraft is dramatically quieter than a helicopter, quiet enough that, according to the company's own testing, it's difficult to hear from the ground at typical cruising altitude. Archer Aviation's aircraft, called Midnight, takes a different structural approach, a fixed-wing tilt-rotor design built around a regional air taxi business model. Short hops of 20 miles or less between helipads, airports, and dedicated landing pads, replacing what would otherwise be a car ride stuck in traffic. Outside the US, the picture is different. China's EHang has taken the boldest approach of any company in the world. A fully autonomous, pilotless, 2-seat aircraft, already carrying passengers on limited commercial routes in parts of China under a type certificate issued by Chinese aviation regulators. Germany's Volocopter has pursued a similar path in Europe, focused on short urban hops in cities like Paris and Rome. Every one of these aircraft shares the same underlying idea: electric motors, vertical lift, distributed propulsion, and, eventually, a level of automation that could reduce or even eliminate the need for a human pilot. Here's what most flying car coverage gets wrong. The hardest part was never building the aircraft. Prototypes have been flying successfully for years. The hardest part is convincing a national aviation regulator that a radically new kind of aircraft is as safe as a commercial airliner. In the United States, that means the FAA's 5-stage type certification process. As of mid-2026, Joby Aviation has advanced further than any other US eVTOL company, reaching Stage 4, the intensive testing and verification phase, with FAA-observed test flights already underway. Archer Aviation is following a similar path with its own aircraft. Neither company had received full US type certification as of this recording. Both have stated a target of achieving it before the end of 2026, though the FAA itself has been clear that final timing depends on the outcome of testing, not on a company's announced goal. This distinction matters. A company's press release is not the same thing as a government safety certificate. Boeing's 787 spent years in a comparable final certification phase. These aircraft may move faster, given how much flight test data already exists, but may is doing real work in that sentence. Even after certification, 3 engineering challenges remain. The first is battery energy density. Jet fuel still packs roughly 40 times more usable energy per kilogram than the best lithium-ion batteries. That's why every current eVTOL is limited to short hops of well under 200 miles. Cross-country flying cars remain for now, outside what the physics allows. The second is redundancy and failure modes. Regulators require that these aircraft survive the failure of any single critical component, a motor, a battery pack, a flight computer, without endangering passengers. Distributed propulsion helps, but proving it under every conceivable failure scenario, in a way a regulator will accept, is exactly what these years of testing are for. The third is noise and public acceptance. Even at reduced volume compared to a helicopter, hundreds of aircraft taking off and landing across a city raise real questions. Neighborhoods will have opinions about. Questions no engineering team can answer alone. Here's the part almost nobody talks about. As of early 2026, no US city had issued a construction permit for a dedicated eVTOL landing pad, a vertiport, anywhere in the country. You can certify the safest aircraft on Earth, but if there's nowhere legal to land it, it never leaves the hangar. Building a vertiport network means solving problems that have nothing to do with aerospace engineering: zoning approval, electrical grid capacity for rapid aircraft charging, air traffic integration with existing helicopter routes and airports, and public buy-in from residents who will live under the new flight paths. Some analysts now argue this ground-level infrastructure problem, not the aircraft itself, is the true bottleneck standing between today's test flights and a genuine flying car era. So will you actually be able to book a flying car ride in the next few years? In select cities, for select routes, at a price closer to a premium car service than mass transit? Quite possibly yes, starting with limited launches in places like Dubai and parts of the United States. A flying car in every driveway, the way 1950s magazine covers imagined it? Not yet, and maybe not ever in that literal form. What's actually happening is arguably more interesting. Engineers have quietly solved a 100-year-old propulsion problem, and the aircraft are, for the first time in history, no longer the limiting factor. The next chapter of this story won't be written by aerospace engineers alone. It'll be written by city planners, electrical grid operators, and regulators. The sky is genuinely closer than it's ever been. What we build underneath it will decide how fast we get there. If you want to understand the engineering shaping the next decade of how we move, build, and live, subscribe to Engineered Future and hit the bell so you don't miss what's coming next.